In Istanbul, a dome 31 meters across has been hanging in the air for nearly 1,500 years. In Chartres, a stained glass blue glows from a window made in the 12th century, and no glassmaker in the world has reproduced its exact tone. In Beauvais, a cathedral vault rises 48 meters above the floor, higher than any Gothic interior ever built before or since. These buildings were raised by men who had never read a structural engineering textbook, who did not know the word stress in our modern sense, and who worked with stone, mortar, and rope. Today, 5 medieval buildings that, by every rule modern engineering teaches, should have collapsed centuries ago. Every one of them can be visited. Every one of them is documented in the historical record, and every one of them was built using methods their builders did not write down, because they assumed the next generation of hands would remember. The textbooks were written long after those hands were gone. Item 1, Hagia Sophia, Constantinople. The year is 537. Emperor Justinian walks into a cathedral that has just been completed in 5 years and 10 months. An absurd timeline for a building of its scale. He looks up at a dome 31 meters wide and 55 meters above the floor. According to one chronicler, he says, "Solomon, I have surpassed thee." The mathematicians who designed the building, Anthemius of Tralles and Isidore of Miletus, were not architects in our modern sense. They were geometers. They had no formal theory of compression, no calculation of lateral thrust, no equations for the weight a pendentive could carry. They had ratios, drawings, and a willingness to try. The dome itself is the part that should not be there. It is supported on 4 pendentives, curved triangular sections of masonry that transfer the weight of a circular dome onto a square base. Pendentives existed before Hagia Sophia. They had never been used at this scale. The dome is so thin in places that light passes through cracks in the mortar. It rests on a ring of 40 windows, which means the structure that holds up 600 tons of brick and mortar is, visually, almost not there. Visitors in the 6th century described it as a dome suspended from heaven by a golden chain. The metaphor was rhetorical. The engineering it describes is real. Notice this. The original dome collapsed in 558, 21 years after the building was completed, after an earthquake. The replacement, designed by Isidore the Younger, has stood since 562, through dozens of earthquakes, including the 1999 Istanbul quake that brought down modern reinforced concrete buildings within a kilometer of the cathedral. The mortar used in Hagia Sophia contains a binder, modern materials scientists are still studying, lime, brick dust, and an organic component that seems to have allowed the mortar to flex rather than crack. No modern restoration mortar has matched its longevity. Conventional architectural history says the dome stands because of the buttressing system added in later centuries. The reading is partial. It does not explain why the original 6th century structure survived multiple major earthquakes before any of those buttresses were built, why the mortar resists cracking under loads that fracture modern concrete, or how a 5-year construction schedule produced a building that has outlasted every cathedral built to imitate it. How do you raise a 31-meter dome in 5 years in the 6th century without a single line of structural calculation as we understand it? Bridge. From a dome that should have fallen, we move west and 4 centuries forward to a window that should have faded. Item 2. Chartres Cathedral. If you find that ordinary documentaries tell this kind of story too flatly, this channel goes where the textbooks stop. The subscribe button is how you find more cases like this. Now, to a town in northern France where a blue has been glowing for 800 years. Chartres, northern France. The cathedral as we see it today was built mostly between 1194 and 1220, 26 years, for a building of 220 meters of length, 37 meters of vault height, and 176 surviving stained glass windows of the medieval period. The stone vaulting alone should have taken longer. The glass alone is the mystery. The windows of Chartres are dominated by a deep, luminous blue that art historians and conservators call bleu de Chartres. It is found nowhere else in surviving medieval glass at this saturation. The glass was made between roughly 1200 and 1235 in workshops whose locations remain debated. The exact recipe is unknown. We know the glass contains cobalt, the standard medieval coloring agent for blue. We know it contains soda-lime composition typical of its period. What we do not know is the trace metal balance and the firing conditions that produced its specific optical depth. When light passes through the glass at certain hours of the morning, the blue appears to glow as if lit from behind. Modern restoration glass, made with cobalt and the best available period-accurate techniques, does not reproduce the effect. In 1939, as German forces advanced into France, the windows were dismantled pane by pane and hidden in the surrounding countryside. After the war, they were reinstalled. In the decades since, conservators have replaced individual broken panes with newly manufactured glass intended to match. The replacements are visible. They are the wrong blue. Even glass made with chemical analysis of the medieval samples, fired in modern kilns, fails to glow. The recipe was passed master to apprentice in workshops that no longer exist. No surviving manuscript records the firing temperatures, the cooling rates, the trace impurities in the medieval sand and ash. By 1300, the technique was already in decline. By 1500, it was gone. The blue you see in Chartres today is the blue that has been there since the early 13th century. The reason it has not been matched is not that no one has tried, it is that the people who knew how to make it died without writing it down. Official conservation literature acknowledges the gap. It frames the loss as a normal feature of pre-industrial craft transmission. The framing is reasonable. It does not explain why the chemical analyses of authentic medieval Chartres glass yield a profile that, when reproduced in modern furnaces with the same inputs, comes out a different color. 800 years, same window, no reproduction matches it. Bridge. Chartres is 26 meters of vault. The next cathedral tried to go higher. It tried to go too high. Item 3. Beauvais Cathedral, Picardy, northern France. Construction begins in 1225. The Bishop of Beauvais and his chapter make a decision that, in the language of medieval Gothic, is open ambition. They will build the tallest cathedral choir in Europe. The vault will rise to 48 meters above the floor, 6 meters higher than the previous record at Amiens, 11 meters higher than Chartres. The choir is completed in 1272. For 12 years it stands. It is the tallest interior space in the medieval world. In 1284, the vault collapses. Quick aside, drop your country in the comments. I am genuinely curious how far this story has traveled and whether you have stood inside a building that should not be standing. Now, back to Beauvais, where the builders did something the textbooks of structural engineering still find difficult to explain. The collapse of 1284 is the first known catastrophic failure of a high Gothic vault. Modern structural analysis, performed in the 1990s with computer modeling, has identified the cause. The piers supporting the vault were too slender for the loads they carried, and wind oscillations at that height set up a resonance the building could not absorb. The rebuilders of the late 13th century did something remarkable. They did not abandon the project, they did not reduce the height. They added intermediate piers, doubled the flying buttresses, and rebuilt the vault at the same 48 meters. The reconstructed choir has stood since 1337. Then they tried to build the transept. The transept tower of Beauvais was completed in 1569. It rose to 153 meters above the ground, taller than the Great Pyramid of Giza, taller than any building in Europe at the time. It stood for 4 years. In 1573, on Ascension Day, after the procession had safely left the building, the tower collapsed. The cathedral has never been completed. The nave was never built. The choir and transept stand alone, propped from outside by an emergency bracing system installed in the 20th century, after engineers determined that the surviving structure was at the edge of what its piers could carry. Here is what the engineers found when they modeled it. The choir of Beauvais, as it stands today, is operating at approximately 95% of its theoretical structural failure load. It should not be standing. The reason it is standing, according to the modeling, is the specific composition of the original mortar and the geometric arrangement of the buttressing, a configuration that distributes load in a way modern simulations did not initially predict. The medieval builders did not calculate this. They built it, watched it fall, and rebuilt it more carefully. The result is a cathedral that, by every modern margin of safety, fails, and that has been standing for 7 centuries anyway. Conventional architectural history calls Beauvais a cautionary tale about Gothic overreach. The reading is true. It does not explain how the rebuilders, working without calculation, produced a structure that operates at the edge of physical possibility and remains standing. What does it tell us that the medieval mind could feel a load distribution, our equations only verified 800 years later? Bridge. Stone is the material we expect to last. The next building is made of wood. It is older than 3 of the 4 cathedrals we have just walked through. Item 4, Borgund Stave Church, Western Norway, the Lærdal Valley. The year, by dendrochronology of its core timbers, is approximately 1180. A small wooden church is built using a method called stave construction. Vertical posts of pine, joined without nails, sealed with tar made from the resin of the same pine species. It is one of approximately 2,000 such churches built in Norway between roughly 1100 and 1350. By 1900, only 30 remained standing. Borgund is one of them. The church should not exist. Wood does not last 846 years in a Norwegian climate. The valley sees heavy snow, heavy rain, and temperature swings of 50 degrees Celsius between summer and winter. Wooden buildings in this environment, as a class, are reduced to compost within 2 centuries unless continuously rebuilt. Borgund has not been rebuilt. The original timbers, the staves that give the architecture its name, are still in place. The original tar coating, reapplied at intervals using a recipe passed locally for centuries, is still doing its work. The recipe is the part that almost vanished. Norwegian tar, the specific formulation used on stave churches, is produced by slow combustion of pine roots in a sealed earthen kiln over 5 to 7 days. The output is a viscous black liquid with antifungal, antibacterial, and waterproofing properties that exceed those of modern wood preservatives. By 1950, only a handful of producers in rural Norway still knew how to make it. By 1990, the number was 3. The Norwegian government, recognizing that the loss of the recipe would mean the eventual loss of every surviving stave church, funded a documentation and apprenticeship program in the 2000s. The recipe has been preserved. It cannot be reproduced industrially. The chemistry depends on the specific resin profile of slow-grown northern pine and on combustion conditions that vary by kiln and operator. Official heritage conservation literature accepts that medieval Norwegian tar is empirically superior to modern alternatives for this specific application. It does not have a complete theoretical explanation for why the polyphenolic compounds in the tar interact with the wood in ways that materials science has only begun to characterize. What is known is that without the tar, the church would have decomposed by 1400. With the tar, it has survived to 2026 and shows no structural signs of being near the end of its life. The medieval builders did not know what a polyphenol was. They knew that tar from this kind of pine, made this way, kept the wood alive. Of the cases we have walked through so far, has any one of them changed your picture of the medieval world? Hold that thought. The next case is the one most engineers wish would go away. It is also the one with the cleanest evidence. Bridge. From a building that survives because of a recipe, we move to a building that survives because of a single decision its builders made, and that no modern structural engineer would now permit. Item 5. Salisbury Cathedral, Wiltshire, England. The cathedral is built between 1220 and 1258 in a remarkable 38 years. The only major English cathedral constructed almost entirely in a single architectural style. Then, between 1310 and 1330, the chapter makes a decision. They will add a spire, not a modest one. A spire of 123 meters, which when completed will be the tallest in the world. It will hold this title for over 200 years and remains the tallest church spire in the United Kingdom. The spire weighs approximately 6,400 tons. It sits on 4 piers that were never designed to carry it. The original cathedral was built without the structural anticipation of a spire of this scale. When the spire was added in the early 14th century, the piers visibly bent under the load. They are still bent. Standing in the crossing of Salisbury Cathedral, you can look up at the 4 supporting columns and see, with the unaided eye, that they curve inward. The deformation has been measured. The columns are between 75 and 110 millimeters out of vertical. They have been in this state since approximately 1330. In the early 15th century, the master builder Richard Farley added internal stone bracing arches and external buttresses to halt further movement. In the 17th century, Christopher Wren, the architect of St. Paul's, surveyed the cathedral and concluded that the spire was at the limit of what the foundations could carry, and that no additional weight should be added. He installed iron tie rods in the spire itself. They are still there. The spire has not moved measurably since the late 15th century. This is the part the engineers cannot fully explain. The foundations of Salisbury Cathedral are under 1.5 meters of soil on a bed of gravel and clay. Modern soil mechanics says that load on this foundation type, at this magnitude, should have caused continuing settlement. It has not. Surveys conducted between the 1668, Wren, 1737, 1951, and the most recent in 2019 show that the spire's tilt, currently about 75 centimeters off vertical, has remained essentially unchanged for the past 3 centuries. The structure has reached an equilibrium that the calculations do not predict. Modern conservation reports describe Salisbury as a building that should not be standing by current engineering standards. The phrasing is direct. It does not explain what the medieval builders sensed about the load behavior of clay subsoils that allowed them to add 6,400 tons to a foundation that, on paper, should have failed. They did not have geotechnical reports. They had the same tools that built Beauvais and Burgund and Chartres and Hagia Sophia. They had a feel for how stone behaves over time, transmitted in workshops, never written down. In each of these 5 cases, the artifact survives. The method does not. We have a dome that resists earthquakes its modern imitators cannot resist. A blue glass that has not been matched in 8 centuries. A vault that operates at 95% of failure and refuses to fail. A wooden church that has outlasted every reason it should have rotted. And a spire that the calculations do not allow, but the building does. None of these requires aliens. None of them requires Atlantis. All of them require an admission that is harder to absorb. Medieval builders worked with a body of practical knowledge: feel, timing, mortar consistency, kiln temperature, tar chemistry, stone selection, that was never fully written down. They assumed the next generation of hands would carry it forward. For a few centuries, the next generation did. Then the workshops dispersed, the masters died, and the pages we now turn to in our textbooks were written by people who had never stood beside one of those masters at the bench. We do not have a knowledge gap, we have an apprenticeship gap. The buildings remember what the books were never given the chance to record. 5 buildings, 5 centuries, 5 workshops whose techniques were never written down, because the people who knew them assumed they would never need to be. Of the 5